Welcome back to ARTS. In this video we'll be going over inclined planes, how to split gravity, how to tilt axes, and how this will help us in our future videos where we go over ramps and pulleys on ramps, so we know how to solve each type of problem regarding force. So an inclined plane is a plane that exactly what it sounds like. It's inclined at an angle, okay? And a block might be dropped here and might be going down or might be pushed up. Doesn't matter. Something is traveling on an inclined plane, okay? And then how would the force of gravity act then? You have to remember, the force of gravity always acts straight down, okay? The normal force is perpendicular to your surface. So if your surface looks like this, your normal force will look like this. But your force of gravity is always going to be straight down. It doesn't care about perpendicularness, okay? So it's always going to be just straight down to the earth. But then we can split gravity, right? Because it's not just straight down. The block is angled slightly different. So we have to split gravity. So at what angle? At theta. So you look at this theta, okay? Using similarity and triangle rules, this theta is going to be the angle between this and this, okay? Between mg, the vector straight down, and mg cosine theta. And then this sine vector here, it's just going to be, you can transpose it here, okay? So the cosine of this angle is going to be equal to x over hypotenuse, right? So what is adjacent here? This thing over mg. So in order to find the adjacent side, it would just be mg times cosine theta, right? Mg here, even though it doesn't look like it, is actually the hypotenuse, okay? Imagine if you tilt your head a bit and look at it like this is a straight line. Then you can understand that mg is facing downward, but it's connected to both ends of these two, right? That's why it's the hypotenuse. So mg times cosine theta would be this vector, and mg times sine theta would be this thing over here, this parallel component. So we have names for these, okay? We don't just call them x and y. This mg cosine theta is the perpendicular component. Why is that? Well, you can understand why, right? Because it's perpendicular to the surface of the block. Not the surface of the block, but the surface of that the block is on, okay? It's perpendicular to that. It's going at a 90-degree right angle there. That's exactly why it's going to be mg cosine theta, and it's going to be called perpendicular component, okay? And mg sine theta is going to be this component, the opposite component, and that's going to be your parallel, because it's going to be parallel with the block's movement. If the block's movement is like this, then it's going to be parallel with that, right? So the parallel component of gravity. Now, what about the normal force? Remember when I told you normal force is always perpendicular to the surface, right? So we know that's going to be over here. But then, in order to balance out mg cosine theta and the normal force, they have to be equal, right? The normal force has to be equal to mg cosine theta so that they both cancel out and the block doesn't fall through the ramp, or the normal force doesn't push the block up. So that's why n doesn't always has to be just mg, okay? That's why I said that sometimes it could be mg cosine theta or something. So mg cosine theta is going to match up to n here, normal. So even if I erased this and I replaced it with a vector pointing this way, you can still see it's the same thing, right? I mean, the gravity vector is going to point downward because gravity is pointing downward. So to match that, n has to go the other way. So while it may be opposite in direction, it is same in magnitude. So N, the normal force, is equal to mg cosine theta. And both of these are the perpendicular component of gravity, okay? So that's why N, the normal force on a ramp, is a bit different than the normal force on regular ground, okay? And then looking at this here, this parallel component, so the normal force and mg cosine theta balance out, okay? There's nothing else to stop. But what's stopping mg sine theta, the parallel component that's moving the block along the ramp? Nothing, right? That's what's going to be a component driving your action. Mg sine theta, or the parallel component, is going to be driving movement here, okay? Because normal and mg cosine theta cancel out. So the part of mg, or mg sine theta, is the only part, the parallel part, that's driving movement. Okay, that's the only force there. That's why acceleration is occurring. So theta, you can understand why, right? Because theta is here. Theta is opposite over hypotenuse. Mg is hypotenuse, so mg times sine of theta is opposite. Similar to vectors, right? So once again, to reiterate, into the surface perpendicular is mg cosine theta. Down the slope or parallel is mg sine theta. And perpendicular is also the normal force. Okay? Alright. So and also this angle over here, through triangle similarity, is the same as this angle over here. That's why we can use this angle to tell us our gravities. Okay? And like I said, normal force is mg cosine theta. Okay? Not mg because it's perpendicular to the surface. And if gravity runs straight down, only the perpendicular component of gravity will interact with normal. But then what's leaving mg sine theta? Nothing, right? Mg sine theta is what's going to drive your acceleration. So A is just as g sine theta, because if net force is equal to ma, right? And then the only force we have here is mg sine theta. So we can say that's equal to ma, right? M divided by m, g sine theta is equal to a. Okay? So very similar to how it canceled in free fall, right? Very similar to how mass doesn't matter when you're looking at free fall and when gravity is the only force acting on an object. What matters is the angles and all those other things. Okay? So pretty neat, right? You'd never thought gravity could be broken into parts. And the normal force could be different. So let's try an example. A 2 kg block slides down a frictionless 30-degree incline. So the angle here would be 30 degrees and no friction, okay? Find A and N. So acceleration, there's no other force acting on it, right? Mg cosine theta and the normal force here are going to cancel out. So only mg sine theta is the net force, okay? So mg sine theta is equal to the net force, or ma. Since I can divide by m on both sides, what is g sine theta? 9.8 times sine of 30 degrees, which is 1/2. So this is going to be 4.9 meter per second squared. Okay, that's your acceleration. Now what's your normal force going to be? It has to balance out mg cosine theta, right? So normal is equal to 5 kgs, because 2 kgs, because that's the mass of the block, times g, 9.8 meter per second squared, times cosine of 30 degrees. So if I pull out my calculator to do this, this should give me around So first 2 kgs, right, times 9.8 times cosine 30. So around 16.97, yeah, just 97 newtons. Okay, so obviously normal force is not equal to mg, okay? That's why you have to be careful here. Mg cosine theta is equal to n, which is a normal force, but they're not the same thing. They're just, mg cosine theta is a component of gravity in the perpendicular direction, and normal force is what balances that component out in the opposite direction. They just have the same magnitudes, and they're equal, but they're not in the same direction, okay? And then acceleration is just acceleration. But what if you add friction onto the incline? Then things get a bit more complicated, right? You have gravity here, mg, force of gravity. You have mg cosine theta, which is going to cancel out with the normal force here. And then you have mg sine theta, which is going to drive your action. But you have friction, that's going to not, then mg sine theta is no longer just going to be your ma, right? It's not the only net force. That's why you're going to have to subtract friction to get your net force. Okay? So it's going to become net force, which is ma, is going to be mg sine theta minus the force of friction. And if you remember what the force of friction was for kinetic friction, it was equal to mu k, coefficient of kinetic friction, times the normal force. And do we know what the normal force is here? Right? That's mg cosine theta. So do you see? Usually you would have just found out gravity and then you would have did mu k times gravity. But in this case you had to understand that gravity is not the one driving it, right? It's the normal force. So mg cosine theta. So pretty tricky concept there. Mg sine theta minus mg sine theta minus mu k times mg cosine theta is equal to ma. M can still cancel out everywhere here because m is in every term. A is equal to g times sine of theta. So if I factor out the g here, the g is also over here, right? So it gets factored out as well. Minus mu k times cosine theta. There you go. That's your acceleration. As always, you don't need to memorize this, right? It's very intuitive. You can figure it out by yourself. So I don't memorize it either. I was just looking at the equations and I was just seeing, oh, how can I make this work so I can get a sort of equation. Okay, so let's try a few problems. A 2 kg block slides down a frictionless, no friction, 30 degrees incline. Find acceleration and normal force. So 30 degrees here, right? It's going to slide down here. So this way. What's your acceleration and what's your normal force? So we know that we have gravity acting here, mg, right? And then we have normal force pulling this block up to match what force? Mg cosine theta. And so these forces are going to cancel out. We're going to be only left with gravity's parallel component, which is mg sine theta. Okay? Mg sine theta is equal to our net force, which is equal to ma, right? Because this is net force. And mg sine theta is the only force here. The other forces have cancelled them out. So mg sine theta is the entire net force. Net force is equal to ma. M's can divide on both sides. And acceleration is equal to 9.8 times sine of 30 degrees meter per second squared, or 4.9 meter per second squared. Okay. And then what about normal force? Well, normal force, you know what we need to do, right? Normal force has to cancel out with mg cosine theta, which means normal force is equal to mg cosine theta. M is 2 kgs. G is 9.8 meter per second squared times cosine of 30 degrees, which is equal to 2 times 9.8 times cosine of 30, or 16.97 newtons in this direction. Now the same block has a kinetic friction coefficient of 0.2. Find its new acceleration. Okay, so let me draw my new forces here. What forces do I have? First we have mg, right? Then we have the perpendicular component of gravity, mg cosine theta. Then we have the parallel component, mg sine theta. The perpendicular component is going to cancel out with normal, so the block doesn't sink anywhere. And then mg sine theta is going to drive our action, but kinetic friction, force of friction, is going to oppose our direction of motion. So my net force is equal to mg sine theta, because normal force cancel out with mg cosine theta, right? So mg sine theta and F friction are left. Mg sine theta minus force of friction, because force of friction is in the opposite direction. So I know I can substitute net force with ma. It's equal to mg sine theta. You remember what force of friction was? Mu k times the normal force. So ma is equal to mg sine theta. And if you remember what the normal force was, that was just equal to mg cosine theta, right? So a lot of m's and g's, right? M's can cancel out here. I can factor the g out. A is equal to g sine of theta minus mu k cosine of theta. And if I substitute in what I need to substitute in, A is equal to g is 9.8 times sine of 30 minus 0.2 cosine of 30. So let me try and see what these make. Times cosine 30. So this should give me A is equal to 3.2 just 0 meter per second squared. Okay, which makes sense, right? If I have friction, my acceleration is obviously going to decrease. Although I didn't expect it to decrease by this much, from 4.9 all the way down to 3.2. That's a lot. So let's try some more problems, okay? I mean, obviously the more complex problems and the ramps involving pulleys will be in my further YouTube videos, as well as auxiliary.com. A 3 kg block sits, so let me make sure this is 3 kg, okay? Sits motionless on a 20 degrees incline, held by static friction alone. Find the minimum coefficient of static friction required. Okay, so I know that mg cosine theta cancels out with the normal force, right? Mg sine theta is driving my action, and we have force of friction opposing my action. So mg sine theta minus force of friction has to be equal to 0, right? Because then I have 0 net force and I'm not accelerating, and I'm motionless. Okay, So of course the force of static friction can be larger than this, but to find the minimum we need to match it exactly, right? To remind you of how force of static friction works, it matches the output we give, so it doesn't expend more energy. And only when we give a lot of force is it gonna bow down and it's gonna break up, okay? So for now, that's why we're saying minimum, because we don't know whether this is the maximum force static friction, right? We just know that this is the minimum. So mg sine theta minus mu k, or mu s actually this time, times n, which is mg cosine theta, right? Because this is the normal force. Has to be equal to 0. You can divide both sides by m, divide both sides by g, and then sine theta minus mu s cosine theta is equal to 0. So sine of 20 degrees, I can subtract that from both sides to make it negative, is equal to negative mu s cosine theta. And then I can divide both sides by cosine theta. Negative sine 20 divided by cosine 20. And since I have a negative here, I can just cancel that out here. So I should get a coefficient of 0.36, and that's just a ratio, so it doesn't have units, okay? So like I stated before, mu static could be larger, which means we could have a larger force of friction, static friction, because it just matches my output. I don't know whether this is my max output. I don't know whether this is the max static friction it can have. But for now, that's just what it's going to match, how it's going to match. Okay, so 0.36. Find the component of a 50 Newton weight acting down on a 40-degree slope and the component pressing into it. Okay. So 50 Newton weight means, you remember what weight meant, right? Weight means the force of gravity. That's why it's different from mass. Mass is just how much stuff you have. Weight is the force of gravity, or mg. So my force of gravity here is 50 newtons. Okay, so that means 50 newtons is my force of gravity. Yeah, that's it. So I could do mg, and then I could find, because I know gravity is 9.81, I could find the mass, but I don't think I need the mass right now. So I'm just going to keep it that way. Okay? But you could find the mass. What is the component acting down a 40-degree slope? That's going to be the parallel component, right? Because if you draw this, if you make a triangle out of this component is this component, which is the sine component, because it's the opposite of this angle, right? Of theta. So mg here, mg cos theta, mg sine theta, and the theta is over here. Okay, so the component acting down a slope will be 50 newtons sine 40 degrees, which is 32.14 newtons. Okay, this is parallel. Perpendicular is 50 newtons cosine 40 degrees. Okay, because that's going to match up the normal force and it's going to be the adjacent side. So that means this is 50 times cosine 40, or 38.3 newtons. And this is going to be the component pressing into it, because that's the component pressing into the slope, right? The ramp, right? And that's all I have for inclined planes. Next video will be going over ramps and how to find, same kinetic friction, static friction, gravity, mass, all of those using ramps, and more complex problems like ramps involving pulleys as well. So make sure to stay tuned for that, and give me a like and subscribe if I help you, so I can help others and continue my content.